Start recording in the cloud. Good. So if you see my screen, I hope so. You should see today we are talking about guidelines for automation systems design. And I tell you, it's going to be mostly about the requirements for automation systems. So we will talk about safety of people, safety of things, and requirements in terms of documentation, readability, and let's say reusability of the code by someone who was not involved in the initial design phase. And we will talk about some guidelines for software design. And in the second part, we will take a specific look at some norms, at some regulations, which are issued by the International Electrotechnical Committee. I think it's useful when you deal with industrial applications. And since you are mechanical engineers, you will tend to work in an industrial environment. Again, it's good you have a look at what's required from the systems you design and what commitments you have to fulfill when you design a system like this. In this case, it's an industrial automation system, but you can apply the same logic to everything else, basically. So let's start by talking about requirements for PLC programs. As we have seen in the past lectures, you know that PLCs are used to control potentially complex and or hazardous machinery. And for this reason, some special precautions must be taken in the implementation of PLC programs. In particular, again, just reading, but we will have some discussion about that. In particular, it is necessary to ensure, first of all, the safety of people. So the first thing you want to be sure of is that people around the planet is safe. You don't want to harm anyone. I don't know if you remember, there was a few years ago, a news about an operator who died into a plant. I think it was from BMW or Volkswagen, something like that, because he was interacting with a robot who was not properly switched off, and he was not taking precautions, and he got like slammed by the robot arm. And I mean, it was a news that spread quite fast, and I mean, this is something you want to avoid, of course. So first thing, safety of people. And we've seen that also when we have seen the example of SCADA from the DTT project. I don't know if you remember that. We took a look at the Green Book, at the interim design report from the DTT tokamak project. And if you remember, in the SCADA system, I mean, there was the overview of the control system, including a SCADA. And among the systems, there was a critical life safety system that was the protection system, the operator protection system. I don't remember the exact name, but they had some acronyms. And you remember that in that case, you had real-time requirements, you had redundancy of the elaboration units, and so on and so forth. So, second thing, apart from avoid harming people, we want to avoid damaging things. So we want to avoid at all costs. Oh, sorry, I think the slide changed for some reason. Okay, we want to avoid to break anything if possible, unless that means saving someone's life or something like that. I mean, you can have some sacrificial components in some cases, but in general, you want to avoid damage to things, and in particular, you want to avoid any kind of damage that can cause long operation time, like long stops in the operation times to put the plant back to work again, or high costs, higher maintenance costs. So the criterion in this case is to limit whatever unavoidable damage to things you might have to cheap repairings and fast repairings. That's, for example, the reason why when you have a PLC, all the outputs are insulated from the field. Like in that case, you can burn one contact. Maybe you can break one photodiode in the contact, but you are not breaking the electronic behind that. So you just change the wire, you change the address, and you can continue operating without having to change the component. So dismount the PLC, mount it again, load the program, test everything, do the wiring from scratch, and so on. Third, of course, you want to ensure the desired operation of the machine. And notice that until now, we have been talking about how to make a system operate in the desired way, in the way we want it to work. And this was the main focus of all of our efforts until now, but this is just third in terms of priority. You have first safety of people, then you have safety of things, then you have your desired behavior. So programming your machine is just, I mean, it's subordinated to more, let's say, more important issues such as, again, avoiding damage. I don't know why today PowerPoint is switching slides autonomously. Okay, so fourth, we want to ensure that the machine operates in a reliable and robust way. There is a concept in industrial systems which is called the RAMI, or RAMI, which means reliability, availability, maintainability, and inspectability. This is a paradigm that you can apply to things, to plants, where you want to guarantee that the plant you're designing is reliable. It means it works under conditions which are different from the ones you have took into account. Maybe you've taken into account. It's available, which means that the time, the operation time is the longest possible. Like you want short maintenances, you want to do preventive maintenance in order to avoid, for example, some damage that could take a longer time. Like maybe when you, it's like when you have your car, you bring it to service before it breaks. Like you change the oil, you change the brake pads, you do things that take small time, but avoid longer repairings in the future. And the same applies to industrial machinery. You have the maintainability. Of course, machines need to be easy to maintain. You need to be able to operate them in an easy way, a fast way. And again, inspectability is kind of the same. You need to be able to inspect what's happening in an easy way. For example, if you look at PLCs, all the outputs have LEDs, which indicate if the output is connected in the correct way, if it's working, if data are being transmitted, and so on. That helps you inspect what's happening. If something doesn't work, you can go check on the PLC if that output or that input is enabled or not. And again, this can be done at different levels. So you can have reliability in terms of the wiring. Maybe you want to use, I don't know, double wires for safety critical components. Reliability in terms of the use. So you want to avoid, for example, that unexpected combination of input can provide some unexpected output. Reliability in terms of programming. So again, you want to be sure that your code is verified, that you did all your tests, that there are no unexpected situations that can occur, and so on and so forth. And finally, last but not least, someone would say, the program needs to be easily understandable to others, because you will probably not be the only person working on it. When you design an automation system, it's very likely that someone else will work on it. Maybe that system goes under maintenance after 3 or 4 years. You are not working in the same company anymore, maybe, and someone else needs to take care of what you did at the time. So ideally, you want to make your program easy to understand also for people who was not designing it in the first place. So documentation is also very important. So in this lecture, we will refer to the norm that you see on the screen, the 60204 part 1. Okay, now this is the Italian norm. You see it's from the CEI, il Comitato Elettrotecnico Italiano, but it's taken from the IEC equivalent norm. It's the general requirements for electrical equipment of machines and safety of machinery. So the norms are basically the same, and the text of the norm is in 2 languages. It's Italian and English. So I reported both so that you have both examples. And here you have a link. If you click on the slides, I will upload the slides to Moodle. You have a link to the PDF of the norm. So this part of this norm, actually, because it's just the first part of a larger set of regulations, provides the requirements and recommendations relating to the electrical equipment of machines so as to promote, first, safety of persons and property. So what we have said before, Second, consistency of control response, so the reliability. And third, the ease of maintenance. Of course, there is no requirement about the correct behavior of the plant here because that's up to the designer. I mean, they cannot regulate the way your plant should work. They can only give you instructions on how to make some specific plants safe, how to make them consistent, how to make them easy to maintain, and so on and so forth. And the only note you have about performance is that high performance is not to be obtained at the expense of the essential factors mentioned above. And you see it's here. So what it's telling you is that, again, all the factors we have seen above, we've seen before, so safety, consistency, reliability, easy of maintenance, easy of, let's say, understanding the program, are the priority. Like, the system should work provided that all the other things have been fulfilled. And this is a very important thing, I feel, because it's quite different from standard programming. I mean, maybe you don't come from the informatics field, so maybe you have little experience in programming, but it's quite usual, at least, I mean, maybe nowadays it's better than in the past, but sometimes code is very badly documented. It's written in a not easily understandable way. Some good programming practices are disregarded in many cases. And sometimes maybe a designer could choose just, I know what inputs, like you could say, I know what inputs I'm going to give to this code, so I'm not treating any other unexpected case. And if you are, I mean, if the code expects an integer variable and you give it a string, you're just going to get some error, which nobody, I mean, God knows what's going to happen. I don't care. Okay, this is what often happens, especially in development phases of code writing. But in the case of mechatronics, in the case of automation systems where machinery is involved, where human operators are involved physically, then you want to be sure that everything is safe, everything is consistent, and everything is easy to understand and to maintain. And of course, okay, I'm talking a lot, but it's just, of course, what you also want to take into account is the economical factor. It's not only the safety, it's also the cost of having a damage, of having an injured operator. I mean, of course, it's bad if he gets hurt, but it's also a cost for who is putting the machines into operations, for example, or maybe damage to products. So if there is some malfunctioning, some products that could come out with some defect, or they could be, I mean, they could have some wrong operation in the chain, and in that case, you are losing money apart from losing, of course, from having safety issues. So if you take a look at the PDF, so at the norm that I was referring to before, one of the first thing you have are these diagrams where it is shown, let's say, an example block diagram of a typical manufacturing system. So let's take a moment to take a look at it. You see that at the lower level, you have your raw material and tooling. So this is where you actually operate on the physical plant. And of course, materials can be transferred. There is some processing equipment which can transfer material from one station to the other. Imagine these as different machines, maybe. And each of these is actuated by some electrical equipment, which is the main concern of this specific document. These electrical equipments are put into communication through local area networks, data link networks, and so on and so forth. We discussed networks in one of the previous lectures. And networks transfer information to higher level controllers. So you might have some operating station interfaced with the controllers, which where again, the operators can choose how the plant needs to operate. They can send information to the plant. This plant goes through the controller communicates over the network and sends the information to the electrical equipment in order to operate on the machines. And also you can have systems or cell safeguards. These are the safety devices, the safety measurements you take. And notice that these can be completely separated from the control system. Like you could have wired safety logics, and again, this could be, for example, imagine the case of a relay of a safety relay switch. It's just cabled onto your system, not passing through the controller. It's just something that switches off the power supply if you have a short circuit, for example. Okay. And of course, in this lecture, we are mostly concerned with this part of the diagram. We are not looking at the specific machines because they depend on the applications you are considering. But the same holds for the electric equipment. You have different actuators, different sensors, different controllers, depending on the application. But the general architecture is more or less the same, and we are considering that in this case. After the architecture of a typical plant, you have the architecture of a typical machine. So, I mean, where machine can be different things in this case. So you see this machine is into a physical environment, its interface to a physical environment, which is described into another section. And it has, again, let's go from top to bottom. Warning signs, item designation, technical documentation, all the stuff that is meant to be, let's say, offline things. Maybe you have some LEDs that tell you have some maintenance to do. You have, I don't know, a flashing lamp if something is moving. You have the documents which go together with the machine and so on. You have a controller which communicates. Maybe this is a system cell control. It could be a SCADA, for example, or a supervisory control that communicates with the programmable controller. This could be a PLC, for example. And here you have all the power supply parts. So you have your actually power supply, which is regulated from in another document. And this goes through a supply disconnecting device, protection against electrical shock, protection of equipment, earth terminal, protective bonding circuit, control circuit, emergency stop, and so on and so forth. This is all the machinery that connects the power supply to the machine itself. And this is mostly for safety, basically. And you see here, each of these has some clause or some paragraph describing it, in this case. This is more from the electrotechnical part, I'd say. Then you have wiring practices, you have testing, you have conductors. Again, all of this is a specific document or a specific part of a document. So there is a correct way of wiring, maybe electrical systems and machinery. There is a way of choosing the cables so that they can carry the desired power, for example. There is a way to stop the automated. Okay, I'll try to pause it and see if it stops. Again, you could have lighting, maybe LED LEDs that signal specific conditions, control circuits, I don't know, earth terminal. This is maybe for if you have any short circuit or something. So this is all from the electrical part. Then we enter in the machine itself. So you might have a motor control equipment if there are motors into your machine with transducers, which tell you what is the position or the velocity of that specific motor. You can have generic sensors and actuators, which have their own interface to the controller. You can have safeguards and warning devices. You can have local operator stations, and you can have emergency stop devices. And again, notice that the stop devices are not connected to the machine or to the controller, but they are connected to the electrical part. Because the main idea is that your emergency device needs to cut off the power. It's not meant to operate on the machine because maybe your PLC could fail or some actuator could fail here. So what you're going to do is just basically unplugging the plug, and you remove the power supply, and that's the safest way of again, making sure that nobody gets hurt. It's like when you take maybe the stairs in the underground, the moving stairs, you have the red mushroom. And when you press that, it's just the power supply to the stairs is disconnected. You are not operating on a controller of that plant. And if you look here, Just there is a wording here. You might recall the CIM pyramid, the CIM pyramid, because you see here we have actuators and sensors and motors. This is like the field level. Then you have your programming, your programmable controller. This is the machine control level. All of these would be what is called the machine level. Then you have the cell controller, which would be what is called the cell level. And then you can have, again, if you go also in the previous slide, you can have higher level controllers with operating stations and coordinating controllers and so on. So this somehow reflects what we have seen about distributed control systems in one of the previous lectures. So now we move explicitly to control devices and see that in this case, the norm that we are examining explicitly refers to the 61131 norm, which is the one we have been talking about for PLC programming. And you see it's here and here, for example. And apart from that, okay, of course, it tells you, for example, that programmable controllers should conform to relevant IEC standards, such as the 61131. And of course, the parts that are cited here are the part 1 and part 2. If you remember, 61131 had something like 6 parts. The part we have been talking about is part 3, which is related to programming. But you also have part 1 and part 2, which describe the electrical components, the general features of programmable logic controllers, and things like that. Second, there is another safety issue. You see that means should be provided to prevent memory alteration by unauthorized persons, and requirements detailed in this paragraph shall apply. For example, if you remember, we told that PLCs usually have a key switch. They have a physical switch from programming mode to operating mode. And if you have a key, then some unauthorized personnel could not go there and just plug in a USB key or some Ethernet cable and change the programs inside the PLC, because you need to physically switch it on the programming mode. Third, we have software verification. Equipment using reprogrammable logic shall have means for verifying that the software is in accordance with the relevant program documentation. Okay, so again, you should be able to verify that the software is working as expected. And for example, if you, like in modern PLCs, you have debugging tools that allow you to check that the right input and outputs are, oh, sorry. I don't know why it's doing like that. Let me try to maybe. Okay, I'll try to close and open it again if it continues doing that. So in that case, you have sometimes some debugging functions that allow you to maybe to switch on some output and see if it's actually firing. And you see the LED lighting up in that case. And that could be a way to check that the program is doing what you expect. So we start by talking about, again, safety of people. So now we go through the requirements one by one. So first is safety of people. The first concern when designing an automation system is the safety of those who work near the control of machinery. And we have already said that. Of course, as we said, safety concerns must be handled preferentially by wired logic. So no passing through the controller, but just physical wires, physical connectors that can be disconnected if needed. And this is discussed into the regulation, into the document we are looking at. And here I'm highlighting some parts that might be of interest. So PLC shall not be used for category 0 emergency stop functions. There are different categories for emergency functions from 0 to 2, I think. These are described later. We will talk about that. Emergency 0 just means is this like the safety critical ones, the very important, the very critical issues that might occur. All the other safety related sub functions, again, the use of hardwired electromechanical components is preferred. So even for non-safety critical functions, wired logic is to prefer. But where programmable controllers are used, then you should take some precautions, and we will see them in the next slide. There is a specific paragraph that discusses them. Of course, it tells you also that the requirements shall not preclude the use of programmable electronic for monitoring, testing, backing up such functions, and so on and so forth. But the equipment shall not prevent the correct operation for those functions. What does that mean? It means that you can actually implement safety functions in your PLC or monitor that safety critical functions are performed correctly. But this should be a way of, let's say, reinforcing the safety measurements. So that should not be the main way of taking care of those aspects, but it can be an alternative way, or let's say an additional way, so that if for any reason the safety logic you have put into place, into action does not work, you also have the PLC helping that, but it's not the main way of taking care of these issues. Next, let me just check. I think there should be a way to avoid it moving on. I don't know. Okay, next, this is the paragraph 9.4, which we were citing before. So general requirements for the control functions in the event of failure. So this paragraph is about what happens if my plant has a failure and what should my controllers do in that case. So general requirements. When failures or disturbances in the electrical equipment can cause a hazardous condition or damage to the machine or to the work in progress, appropriate measures shall be taken to minimize the probability of the occurrence of such failures or disturbances. The required measures and the extent to which they are implemented, either individually or in combination, depend on the level of risk associated with the respective application. So, again, of course, appropriate measures should be put into action to minimize that any failure or disturbance happen. That's trivial, let's say. What you could do is first protective devices. So you can have physical devices protecting the machine. Maybe that could be an interlocking guard. Maybe if you had two switches that could cause a short circuit, maybe you could add an interlock. Or maybe, for example, another thing you might do, let's say you have a machine which has moving parts inside. You could add an interlock where if you open the port of the machine, you switch off the power to the machine. Or maybe you cannot switch on the machine itself if the door is not closed. That's an example. You can have, again, protective interlocking of the electrical circuit. Sorry, I have a guest that is desperately trying to walk on the PC. Again, you can have interlocking of the electrical circuit. You can, of course, you should use proven circuit techniques and components, so just resort to well-assessed techniques. Redundancy is another way of taking care of possible failures. If you have two devices doing the same thing, if one breaks, you still have the other. And again, you can have functional tests. This is another important thing. You should provide some tests to verify that everything is working correctly as expected. Because sometimes, maybe in the best case, protective devices, so devices that are supposed to enter into operation when a failure occurs, are there, but they will never operate because the machine never breaks. So ideally, those devices could break maybe just because of time passing, and you could never notice because they never enter operation. So there should be a way of testing these devices, even if they are not actually working. This is something similar to what you have in your house. If you take the differential switch in the electrical panel, you have a safety switch which can be used to disconnect the power if you have a short circuit somewhere. And in that case, you have a small button that you can press to test that it's working correctly. That's a very simple example, but you got the idea. I think Okay, so again, what is the take-home message? First, programmable electronic devices should not be used for critical safety functions, especially if they are category 0 emergency functions. On the other hand, non-critical safety concerns may be handled through such devices, especially if this is done in a redundant way. So you have a physical handling of those, plus the programmable device taking care of this thing. And again, also in this case, some requirements are provided. And for example, again, we will see what the norm prescribed for emergency stops that we had in the previous slide. I'll tell you it's something that we will discuss later on. So stop functions, here it is. These are the emergency stop functions that we were talking about before. So you see that category 0 is stopping by immediate removal of power to the machine actuators. Just an uncontrolled stop. This is basically for the safety critical things. It's just, you just disconnect everything and everything stops. Category 1 is a controlled stop. So the power is still available to the machine actuators to achieve the stop, and then remove all the power when the stop is achieved. So there is basically a way to tell, okay, I will stop the machine, maybe in a controlled way, and then I disconnect the power. This could be, for example, to avoid damage to the machine. I mean, a typical example that I can think of, not very typical, but an example that I have in mind is that of tokamaks. You have some ways to do what is called a controlled shutdown. If something is going wrong, maybe you hit some current limit, then you have some pre-programmed current waveforms that bring the current to 0, but not immediately. You don't just disconnect, let's say, a few kiloamps current, because then you might have some problem. But then in that case, you ramp the current down, you bring them to 0, and then you disconnect the power supply. Okay, and category 2 is a control stop with power left available to the machine actuator. So you maybe just stop the motors of your machine, but then they are still connected. You don't need to actually unplug. Yes, I have. Okay, someone was asking the simultaneous transcription of the lecture. So again, this is where you don't unplug your machine. By the way, I think just incidentally, this lecture is new. It's not on the neither on the Italian course you have on the on the YouTube channel. So maybe I will upload it. I will try to make it available to everyone, just in case it can be useful. What else? Okay, more emergency stop issues. In addition to the requirements for stop, the emergency stop function has some additional requirements. This is not a simple stop, it's an emergency stop. So first, emergency stop shall override all other functions and operations in all modes. So if it's an emergency stop, it should be highest priority. Second, if power to the machine can cause an hazardous condition, it shall be removed as quickly as possible without creating other hazards. For example, by the provision of mechanical means of stopping requiring no external powers and so on and so forth. Third, if it's an emergency stop, reset shall not initiate a restart. This is, if you remember when we talked about SCADA, you have different kinds of emergency stops or alarms, and you can have alarms where the alarm condition must be removed and the operator must acknowledge the alarm. Here is the same. If you reset the emergency button, usually they have, imagine just the emergency, the red mushroom. When you press it, it locks into the stop position. You can reset it, putting it back, but then it's not starting the machine again. You need to actually start it explicitly. Like you must willingly press some button to make it operate again. And that's, of course, that's just common sense. Imagine someone gets stuck into some machine, you press the emergency stop, then someone else comes along and they maybe press it again because they think it still needs to be pressed, and it unlocks, and maybe the machine starts again and it causes some damage. So that's not how you expect it to operate. If you want to start it again after an emergency stop, then you want to do it explicitly, let's say, on purpose. And emergency stop can only be category 0 or category 1 stops, where the choice is determined by the risk assessment of the machine, of course. Where a category 0 stop is used, only hardwired electromechanical components shall be used, and we have already seen that. When category 1 is used, final removal of power to the machine shall be ensured, but it's just after the stop has been taken care of. Other safety concerns are related to the interface between the machines and the operator.
Excuse me.
Yeah.
Why in the previous slide? Okay, in the category 0, why only hardwired electromechanical components are used?
Because again, we said if you category 0 means it's safety critical. It means you need to immediately remove the power supply to the machine, and you want to do that physically, like you want to cut the power supply.
Ah, okay, yeah.
You want the controller to take care of that. Of course, you can also have the controller telling if this happens, stop everything. I mean, that's not wrong. You can do that, but that cannot be the only way of taking care of that specific category of alarms.
Okay, thank you.
Make sense?
Yes.
Okay, so what are safety precautions?
So, hello, sir. Hello, sir.
Yeah, please.
Yeah, for drives that are controlled by variable frequency drive, and that can you hear me?
Yes, not very well, actually.
Okay, I'm actually saying that for drives machines that are powered by variable frequency drives, variable frequency motor drives, that every command reports to the PLC first. How does the emergency stops work?
I'm not sure I got your question. Yeah, you said you want to know how to stop machines that are only connected to a PLC. Is that the question?
Okay, I'm going to drop the question in the chat.
What's the charts? I'm not sure I got your question. Sorry, I don't hear you very well, actually.
It's better to ask on the chat.
There is a question on the chat. I'm sorry. Okay, let me check. I was wondering. I was trying to interpret that in terms of some automation issue. Let me check if I see it. Where are it? So chat. I see the chat, but I don't see any question. Maybe it was not sent to me.
Like my chat is asking. He wanted to write on the chat. He wanted to ask you on the chat.
You can do that, yeah, sure. Oh, for machines with VFD, how does the emergency stop works? What is VFD? I'm sorry. Maybe I'm not sure about the. What's the acronym? I'm not sure about that. Variable frequency drives with PLC. Okay. Well, so basically you are concerned with electric motors. You want to know like something like asynchronous motors, which have the frequency modulation or something like that. Okay. Well, if I had to guess, let's say, if that's safety critical, so if there is a safety critical issue, you can connect either the power supply of the driver. So if you switch off the power to the driver, then in that case, you can just stop that. Or you can connect the line from the driver to the machine, I'd say. In general, I mean, for this kind of machines, I think what is done is something like, again, if you have moving parts, if you are referring to motors, and I think that's the question. If not, just tell me. Usually motors need to be like, you need to avoid physical access to the motor. Makes sense? Like you have either cells where you have doors. So if you have to walk inside the cell, you need to open the door and disconnect the power to the machine. So machine must be stopped when you are entering the automation cell. Or that could be, for example, if you have, imagine you have a fan, ventilating machine, air conditioning module. Then in that case, you have a box, for example, and you have a door that you can open, a small panel. And in that case, you might have a contact that removes the power. What else? Yeah, again, I think inverters probably, I'm not an expert, but I think inverters, like modern inverters, also have some safety functions. Like they can detect if something is wrong in the power supplies, for example, and they can interrupt the power feed to the motor, probably. But I'm not an expert. I should check. I can let you know if you want. If you are interested in a specific application, I can verify. I don't know if that answers your question. So, okay, safety precautions for the operators. That means you have, okay, you might have whatever you can imagine. So like flashing lights that tells you that something is wrong. You can have push buttons that can light up. So maybe if you have a stop button, that button can have a light and the light can light up if you are stopping the plant. Again, emergency stops. So, you know, on a panel, if you have ever seen like the pendants for industrial machines, they always have the red button that you can press, which is easily detectable. And the same holds for, we will see that, for example, for safety sensors, there are some sensors, and also, again, which may be the buttons, but not only. They can be, for example, barriers where you have light curtains that, it's like a photocell, basically, where if you pass there, it means that you are accessing a potentially hazardous area of the machine, and maybe you need to disconnect the power. In that case, they have a specific color. They are yellow and red. So you see them. You know that that part is an emergency component, a safety component. Again, buttons and indicators, and I'd say also wires, can be standard color coded. So for example, again, emergency and stop buttons are red. Start buttons are usually green. There is a table actually in the document where you know each color or what function each color corresponds to. And again, you can have monitoring and signaling of command actions, moving parts, and so on. So maybe like in the simple example of the gate we were seeing the last day, you have a lamp flashing that tells you that something is moving, for instance. Or maybe think of what's the word for that? You know, that the small cars that are used to lift things in the warehouses. I'm not sure about translation, but I think you got the idea. In Italian is muletto, but I'm not sure in English. They have a beeper. When they move, they just make a sound, a noise that you hear, so that you know something moving is approaching. Okay, and here you have the colors. This is in Italian. No, it's both languages, but you see, like for example, red means hazardous conditions, yellow means abnormal condition, green is normal operation, blue indicates that something is mandatory, white is a neutral that you can use if you don't know what color to use, basically, and so on. So you have a standard color coding that you should follow when designing a plant, an automation plant. In addition, you can have flashing lights, which can be used for different purposes. So they can be used to attract attention, to request an immediate action, to indicate a discrepancy between the command and the actual state, to indicate a change in progress, and so on. In general, it is recommended that higher frequency is used for higher priority information. That's something that maybe is not trivial, but it's like this is a way of telling you how specific these regulations can get. Like even the color of things or the frequency of a flashing light can be subject to a specific, maybe not mandatory norm, but an indication or a prescription or a suggestion that you should implement. Of course, again, another very specific thing is where the devices should be located. Like they should be easily accessible. You don't want to put an emergency button behind something so that you have to walk around an obstacle in order to press it. And they should be placed at each operator control station. So you should be able to stop your plant from wherever an operator is supposed to be. And again, see here, actuators or emergency stops should be red with a yellow background. And usually palm or mushroom head type are preferred in that case. Okay, of course, in some cases, safeguards may be suspended, as an example for maintenance. Again, a typical example here comes from air conditioning systems. Usually, if you have a motor in a ventilating machine, it has a direction of rotation. So it rotates either in one sense or the other. Of course, the motor can rotate in both directions depending on how you plug it, but you want it to rotate into the correct direction for the blades of the fan to work properly. But if you just wired it in a wrong way and it turns in the wrong direction, so how do you know that? You need to plug it, open the door, and look at what's happening, because there's no other way of knowing that apart, like maybe installing some costly sensor, which people don't want to pay for. So this can be a situation where you need to leave the machine into operation, even if that could be potentially hazardous. And in that case, you have some specific, you have some special attention to pay. And again, when it is necessary to suspend safeguarding, a mode selection device or means capable of being secured in the desired mode shall be provided, so as to prevent automatic operation. In addition, one or more of the following means should be provided. So first, a hold to run device or a similar control device. What's a hold to run device? A hold to run device is just something that makes a machine run until it's pressed. So if you want this motor to run, for example, you need to press a button. Sorry, and keep it pressed. This is done, for example, for presses. If you have automation presses, which can be very, very hazardous because you could just like get a hand smashed into that. You have two buttons, so you need to press two buttons together, and they need to stay pressed together in order for the press to work. Otherwise, it's just going to stop. Another thing could be a portable control station, like a pendant, with an emergency stop device, so that while you are operating, you can bring this sort of remote with you, and if something happens, you just press the button and stop the machine. The power of the plant could be limited, maybe, so you don't risk too much. The range of motion could be limited. Imagine a robot, maybe you don't want it to move the full range if there is someone close to that who is fixing something, maybe. Finally, again, other safety precautions can be related to the choice of manual controls. And again, hold to run controls are one possibility. So something where the machine works until the button is pressed. Two-hand controls, so somewhere where you have to keep both hands on a control in order to run the machine. And enabling devices. Enabling devices is maybe you need to switch on some consents, some switches before you can operate the machine. Of course, we are humans, and some operators may nevertheless compromise these commands. For example, if you have a two-button command, you can just lock one of the buttons by, I don't know, stacking some screwdriver in there and press only the other one. So again, additional precautions are always welcome. Maybe these additional precautions could be the ones that the controller is taking care of. So it's not wired, it's programmable logic, but it's some additional thing that can be added. An example, maybe you have a two-hand control. Which is wired. So you have maybe a series, just two buttons in series. So if you don't press both, you cannot power the machine. But maybe you want to check that the two buttons are pressed into a specific time interval. Maybe you want them to be pressed together, or at least you don't want to wait more than 1 second from one to the other. Because if someone needs to take a tool, lock one of the buttons, and then move on the other side and press the second, probably more than 1 second is passing. And in that case, you know that something is wrong and you don't operate the machine anyway. Okay. Okay, here you have a description of this kind of controls. So hold to run controls, continuous actuation of the control device is required. Two-hand control can be of different types. First, concurrent action by both ends. So continuous concurrent action during the hazardous condition. This is used for presses again. Type 2, a release of both control devices before machine operation may be reinitiated. So you need to release them and then press again before you start. And this is the example I was giving you before. Like maybe if someone stops one of the controllers and then press the other, then it lifts the finger. And to press it again, you need to remove the tool and press it again. So you make life harder for people who wants to avoid safety measurements. Or maybe type 3, again, concurrent actuations where you need to actuate the control devices within a certain time limit of each other, maybe half a second. Okay. These are just possibilities. Or again, enabling devices are additionally manually operated control device used in conjunction with a start control and which, when continuously actuated, allow a machine to function. And among the features of these devices, you might want to connect them to category 0 stop or category 1 stop. So what does that mean? Again, this is with manually operated and with continuous actuation. So it means that you have, okay, maybe you have some control device, like some controller that operates a machine. So it's not enough to just switch the power on, but you have a consent, an enabling device, which means that you need to press that for the machine to operate. It's not the power supply to the machine, it's just an enabling device. It's just something that you press to make sure that the machine is running when you want to and not in any other condition. I don't know if that makes sense. Okay, so the next part is damage to property, to things. Any question until now? Is it everything clear? Okay, so second requirement is that a PLC program should be written so as to avoid accidental damage to property. So interlocks between commands that activate different or opposite functions. For example, again, we have seen an example in one of the exercises we made. You might have a start-stop mechanism where you can have a short circuit if you press both buttons together. Then in that case, you can interlock them. So if you press one, you cannot press the other, and so on, and the same, and the opposite. Manual or automatic interlocks. Software interlocks, which render incompatible sequences mutually exclusive. This is like when we have seen the semaphore in SFC, that's a software interlock. If you are in one sequence, you cannot execute the other and vice versa. Of course, you need to manage correctly limit switches, occupied machinery, operating limits, and so on. And again, you need to manage correctly emergency or dangerous situations in general. Just that's a quite general prescription. An example, which we already did, but it's just written here, so let me comment it quickly, is a motor with forward and backward control, where activating both commands may cause a short circuit. This is what we were adding to the exercise for the gate control last lecture. So, contactors, relays, and other control devices that control elements of the machine and that can cause hazardous condition when actuated at the same time shall be interlocked against incorrect operation. And again, also here, proper coordination shall be ensured by suitable interlocks. And also here, where a failure of a mechanical brake actuator can result in the brake being applied when the associated machine actuator is energized, and a hazardous condition can result, interlock shall be provided to switch off the machine actuator. So there are situations in general, I mean, we don't want to be super specific here, but just know that there are situations where you want to put into action either physical or software interlocks to avoid that incompatible sequences are executed together. So that's one of the safety, of the most common safety concerns you want to take care of. Other examples, over travel limits. Maybe you have a machine that cannot run over after a specific position. In that case, you can add a limit switch, which can be a mechanical switch. We will see them. That can maybe disconnect it can either be handled through a programmable device. That's one possibility, or it can disconnect the power supply, maybe through a contactor. Or maybe operation of auxiliary functions. So the correct operation of auxiliary functions shall be checked by appropriate devices. Where the non-operation of a motor or device for an auxiliary function can cause a hazardous condition or cause damage, appropriate interlocking again should be provided. And here, it's everything in control functions in the event of failure. You can see the previous slides where we had some, again, the use of control functions in the event of failure. We did some considerations there that also apply here. We did there for the safety of people. Here they are for the safety of things, but it's basically the same. Third, we said that programs should be documented. They should be easily maintainable and expandable, even by people other than the original developer. We have already said that, and I will repeat that other times. The machine could be sold to third parties, perhaps very far from the company that designed or built it. And in general, it's good practice to organize the programs in a modular, scalable way and to accompany them with a complete documentation. What does that mean? First, if the same function is performed in different places, you want to reuse the same part of code. You don't want to copy paste it again. Second, variables should have self-explanatory names, and these names should be documented. Third, IO variables should have the same names in the system documentation, in the wiring diagrams, and in the program. So maybe if your motor is called, I don't know, motor 1, then you should have a variable in your program that is called motor 1, and your wiring diagrams should report the motor 1 tag. Functions, you should describe the tasks performed by each function, subroutine, program, and in general, you should comment the code. Best practice is to comment both the code and the variable table. So you have a field for each variables to specify what that is, add comments to that, and so on. And this is also regulated into the IEC norm. So again, information provided with the electrical equipment shall include a clear, comprehensive description of the equipment, installation, and mounting, electrical supply requirements, information on the physical environment, so vibration, noise levels, dirt, and so on. Overview block diagrams, if appropriate, like the ones we have seen at the beginning of this lecture. Circuit diagrams, very important. Information on programming, sequence of operations, frequency of inspection, frequency method of functional testing, and so on and so forth. And here, for example, SFC come very handy, because if you have a functional SFC, that's a way of describing how your automation logic works. Description of safeguards, interlocking functions, and in general, emergency equipment here. And description of safeguarding and means provided where it is necessary to suspend the safeguarding. Okay, this is what we were talking about before. If there is a situation in which you want to suspend safeguards for maintenance, for example, you want to describe that in documentation. Not only, you need to provide an operating manual. So technical documentation shall contain an operating manual detailing proper procedures for setup and use of the equipment, with particular attention to safety measurements again. where the operation can be programmed, detailed information on methods of programming, equipments required, program verification, and additional safety shall be provided. What does that mean? In general, okay, the program is embedded into the PLC, but in some cases you can have an interface where the operator can set up some information. So you are not, I mean, what it means is that you're not rewriting the program, but maybe you have some parameters that you can set. Maybe, I don't know, you have a machine that needs to perform a specific trajectory, maybe a cutting tool or a CNC or a robot. Then you should provide the operator with a comprehensive overview of how you need to provide that information to the machine. So how the interface works in this case. And you should have also a maintenance manual. So technical documentation shall contain a maintenance manual detailing proper procedures for adjustment, servicing, and preventing inspection and repair, with documentation of maintenance records and so on. Maintenance records means, for example, you have tables where people annotate when the last maintenance has been performed, who was the operator who performed that, if there is any comment on that, and so on. You sometimes see them. Sometimes it's on the machine, sometimes it can be in the documentation. Maybe you have a maintenance program, which is provided by the machine supplier, and there is a user who signs or puts a stamp when the maintenance operations have been performed. So in general, before you start designing a PLC program, you should consult the applicable documentation and regulations. That's, let's say, sort of trivial. You should become familiar with the system to be controlled. So wiring diagrams, mechanical parts, operating cycles. And in general, it's a good practice to divide the program into sub-blocks associated with well-defined functions, especially for large plants. So let's take a moment to comment this slide. This is in connection with what we have seen about the development cycle and life cycle of an automation system. So in general, who works in the automation field needs to be sort of a transversal professional figure. What do I mean with that? Like in general, if your work is to design automation systems, you will be working with very different applications. These could be chemical plants, electrical plants, mechanical plants, numerical control machines, robots, I don't know, maybe you have some painting, some welding, some inspection, semiconductors, electronics. I mean, you can have very, very different environments. So in general, who works in the field needs to be aware at least of the basics of all these things, or of the fields where he works most commonly. Like, for example, again, in my case, I've been mostly working in tokamaks, so my expertise is on that. So I know something about the sensors and actuators and control systems and control loops that are installed on those machines. But in general, if I worked in the industrial field, maybe I wanted to know something about, I don't know, packaging systems or air conditioning systems or chemical plants. Maybe again, maybe in the food industry, chemical plants are the or again, chemical plants with specific regulations because it's in the food industry needs to be taken into account. So you need to have the message is that you need to have an expertise on the specific type of plant you are going to program. And often this means talking with the people involved in the design of that plant or in the operation of that plant. And I think it changed slide while I was not looking. So you should become familiar with that system. And that means studying wiring diagrams, mechanical parts, operating cycles, expected outcomes or products, possible failure conditions, possible errors that may arise, and so on. And it often also means consulting the applicable documentation and regulations, because maybe, okay, an example, since I'm a bit familiar with the air conditioning environment, I have a simple example in that case. You have there is some regulation for machines for the energy consumption. So you need your machine to be below a given maximum energy, above a given maximum energy efficiency level. So for example, the motors you are plugging to your fan needs to be certified to work at least in 1 point over, I don't know, 97% efficiency. I don't know, I'm just telling a number. I don't remember the exact number. But the idea is like that. And similarly, for example, you don't want your pipes, your tubes to provide very large pressure drops, because that means you need more power to drive the plant. So for example, you want to avoid very sharp bends in that case. And for example, you cannot use very strong filters. I mean, some types of filters are not appropriate to some specific applications because they make you lose a lot of pressure, and that means that you are wasting a lot of energy, basically. So if you are maybe, I don't know, maybe you are working with the air conditioning system of a supermarket, okay, or a mall, then you don't have chemicals to filter, or you don't have very significant safety concerns. You just want to guarantee that the air is recycling. So you will use some filters, but maybe you are not using absolute filters, which are the ones that are used in surgical surgery rooms. Because in that case, those filters are very, very narrow, and they are designed to avoid, for example, bacteria coming into the room. So if you have someone who's going under a surgery and maybe his chest is open wide, you don't want bacteria to fall into that. But if you're just in a mall buying clothes, then that's not a problem. Okay, I don't know if you get the idea. And similarly, for example, you have a different different regulations for conditioning systems for kitchens, for industrial kitchens. Like if you're in a restaurant, then in that case, the problem is that you have bad odors. Maybe you can smell, smell the food smell, the food odor. And then in that case, maybe you want carbon filters to avoid grease or smokes or, again, smells to come out of your air conditioning systems. So it's different applications. The system is the same. It's just basically a fan plugged to a motor and with pipes. But the type of filters and the requirements that are given to the system are different depending on the type of application, okay? Third, divide the program into sub-blocks associated with well-defined functions, especially for large plants. This is, again, connected to the design cycle we have seen in one of the previous lectures. The idea is that you want to like to design your plant top bottom. So you want to divide it into small parts. Then you want to program these small parts and make them operate. You want one single giant program that does everything. You want small sub programs that take care of very specific tasks, and then you want to coordinate them in order to have your full automation system. Okay, that's a way to make your code more readable, to have reusable parts, to document it at a lower level, so you know that what each part is doing, and so on. Of course, you need to find a happy medium. You don't want to make a separate function for everything, but you don't want to have a single program for everything. You need to find a right way to subdivide your software in an efficient manner, let's say. Okay, another thing you want to know is switching on the plant. Often when turning on a machine, it may be necessary to carry out some preliminary operation. And these operations could be software. So maybe you need to initialize variables, reset timers, check the date, maybe to verify if there is any scheduled maintenance, maybe something like that. They could be hardware. So maybe it's preheating if you have, I don't know, holodynaamic machines. Sometimes you need to heat them for the oil to be fluid. Or maybe you have combined functions. So maybe you have calibration, which means that you have a software issue. You need to put the right numbers in the software, but you also need to move parts to measure those numbers. And these procedures could need to be carried out once or periodically. So it's a good idea, especially if that's periodic, to have a special routine that is called at the beginning of operations or periodically. Imagine, like, a very, very simple example is the printer at your house. If you notice, sometimes it undergoes a calibration procedure. You see the printer is moving inside, but it's not printing anything, maybe out of the blue, maybe you are not using it. And sometimes it starts moving, especially the old printers. They start moving and do stuff. Or maybe when you switch them on, they do some operations. That's a resetting and a calibration procedure. Again, what are some examples? Calibration of motion sensors. The example was the home printer I was talking about a moment ago. Loading operating set points stored in some user terminals. Maybe you have some users setting some set points for controllers through a SCADA. You want to get them when you switch the plant on and operate at those set points. Again, oil heating in a hydraulic control unit. These are basically, again, it's like a controller, but it's oil-based, it's hydraulic. That means you usually have a motor which operates a pump, which puts oils into pressure. You have some filters for the oil to avoid dirt going into there. And you have valves, and you can use that to operate systems, not with electrical circuits, but with hydraulic circuits. That's used, for example, if you have explosive environments. Okay, maybe you don't want sparks into your environment, so you don't use an electrical circuit with contacts, but you use oil or hydraulic circuits, and that's a way you can solve the issue. Or it can be used, for example, in presses. If you have a press, often presses work with oil because they are oleodynamic presses, because that allows you to have more power if you use it properly. So in that case, you have an hydraulic control unit that controls that press. Some other example could be the starting of cooling systems. So maybe you have relays for ventilation circuits. You might have some cooling circuit, maybe with water, not with just with air. You can have fans that you need to switch on, and so on. An example is that even in the controllers, maybe you have your rack for your PLC, and those racks are often air conditioned. They have some conditioning system, which may be controlled by the PLC itself sometimes, or at least supervised by the PLC itself. Let me check where we are. I think Zoom is just, sorry. It's like getting a bit crazy. Okay. So I was just fighting with the Zoom bar. Okay, other examples. Again, before starting the machine, you should perform safety checks, which means, again, power verification. So you need to be sure that your power supply is working properly. It can be control of operating parameters, which must be in acceptable ranges. And here is a typo, I think I'll correct that. Here. Must be such acceptable ranges. I mean, again, this means that you might want to check pressures, temperatures, voltages, currents, and all those physical quantities that might cause an hazard, a problem into your device. Again, that is those are all things that you might want to check before starting operation. You might want to verify safety devices. Again, we say that safety devices should work in a wired fashion, but maybe you have devices which are not safety critical and they are operated through a PLC. This might happen in some cases. Maybe you want to verify that they are working as expected. Maybe you want to verify enabling devices. So again, all the ones we were talking about before, all the buttons that maybe you need to press to be sure that a machine operates when you want, as you want, and in full safety conditions. Let's move on. Another thing we have is modes of operation. So machines may have multiple modes of operation, which can be, for example, manual or automatic. That's a possibility. When multiple modes of operation are provided, then you should have a modal operating selector. Maybe you have seen those. The most common are the switches that just that can be placed into different positions. It's like, what's the word for that? I mean, okay, imagine just, for example, the switches in the air conditioning system of a car. For sure you've seen that. You have the ones that can be put into multiple positions. Those are switches that actually provide multiple modes of operation for that specific system. Like in that case, you can have different levels of airflow of power into your air conditioning system and different level of temperature. Conceptually, it's exactly the same. In automation systems, these selectors are hierarchically placed immediately below the emergency stops. So first thing, you have an emergency stop. So you have something that can be operated to stop your plant if any safety critical issue occurs. Then you have a modal selector. So if your plant can operate in different modes, you should select that. And it's usually a physical switch that stays into a given position. And in general, what is prescribed is that this selector does not, I mean, the change in position in this selector does not provoke any action on the part of the machine directly. But it's just a pre-selector. Let's say it's a way you tell your, for example, your controller what specific mode, operation mode should be adopted by the machine. Just let me check. There is something on this slide that is strange. Just let me check that. This on the part. Just do that. Okay, what does that mean? Imagine you have a mode selector which switches from manual mode to automatic mode, for example. It's not that this mode selector does something on the machine. It's just giving an information on your controller, for example, which takes the measurement of the position of the switch and decides how to operate the machine based on the mode that was selected from the by the operator. And this is explained in this part of the document. So each machine can have one or more operating modes determined by the type of machine and its application. When hazardous condition can result from a mode selection, such selection shall be prevented by suitable means, for example, a key-operated switch, an access code, things like that. And again, mode selection, this is what we were talking about, shall not initiate machine operation. There is a separate action by the operator that is required, which means maybe you put your machine into manual mode, then the operator presses start and he can operate the machine. But it's not just putting the selector in that position that puts the machine into operation. Of course, if you have safeguards, this should work for all the operating modes. And again, the document is sending you back to section 924 for what concerns possible conditions in which you need to suspend the safeguards. Sorry. And indication of the selected operating mode should be provided. What does that mean? It means that from outside the plant, it should be clearly visible which is the mode in which the machine is operating. Like if you have maybe a manual and automatic mode, you could have a switch, a physical switch that tells you where you are in that moment. Or maybe you have a light, or maybe you have a visual display indication. Anyway, you should have something that tells whoever is operating the machine what is the mode in which that machine is operating. Because that's, I mean, you don't want to enter the PLC program every time you need to know what a machine is doing. You want to be sure. I mean, you will always want to be able to tell from outside what your plant is doing. That's, again, for safety mostly and for inspectability. So once we have fulfilled all these steps, so we have taken care of the safety of operators around the machine. We have taken care of the safety of things, of property. We have taken care of safeguards, so interlocks, two hands controls, continuous action controls, and all these kind of things. We have our emergency stops, we have our mode selectors, we have documented how we intend to program our plant. We have produced wiring diagrams, mechanical part drawings, I don't know, we have checked the interfaces, we have functional tests, all these things. Then, I mean, after all that, we can actually design the main control logic. Of course, parts of the things I was listing go along with the design of the controller. For example, functional testing is usually done in parallel. Like you design a part of your control logic and you design tests for that, and you move in that way. So the main control logic will call the necessary routines depending on the expected modes of operation and the possible critical situations that are considered by the designer. In general, it is a good practice, again, to subdivide the operations to be carried out in suitable subroutines, which can be dedicated, for example, to different machinery or to different processing cycles. And in many cases, you can have parallel things going in parallel. So maybe you have different machines operating in parallel, also on the same device. And I think about that, we've had most of the course until now, so I won't spend too much time on this point. I think it's okay. Another aspect that needs to be considered is the possibility of power failures. So if the PLC is left without power supply during a machining process, it may be useful to preserve the state of some variables. We have already talked about that, if you remember. Maybe you are in the middle of some operation, power goes off for whatever reason. When you start again, you need to reset your plant, and that can take a lot of time and effort. So in some cases, it's good to take some time to analyze if some specific variables should be preserved in order to avoid a long restoring time after a shutdown. And in some cases, not always, but operations may resume from where they had been left without wasting machine time. Imagine you have, let me think. Imagine you have a packaging system, maybe. So you are just putting, or maybe you have a filling and capping system for bottles, okay? You are just maybe putting things in a box. Let's take the very simple example. And you know that each box must contain, I don't know, 100 pieces. So you have some counter that is counting the pieces that go into that box. Then if the plant stops, you can start right from where it stopped, because you don't have operations that need to be completed. It's just things that need to be put into a box. So in that case, you maybe want to store the count value of your counter so that I was wondering, yes. Sorry, yeah, I was wondering if I had started the recording or not. Again, maybe in that case, if you have this counting machine, you want to store the counting value so that if the power fails, you don't need to start counting from scratch, and so you have maybe a half full box that you need to throw away or to fill manually before you can start. Okay, that's a very simple example, but you got the idea. And in general, the point here is to resume operations from where they had been left without wasting any machine time. Again, we have seen that PLCs generally have persistent memories that can keep a snapshot of the plant at a given time. And that's done through what is called a retained variable, which, of course, must be used properly. And in general, they can be reset if necessary. Okay, so that's pretty much all I had to tell you today about this point. So I will stop recording now, unless you have questions that you want me to answer. Okay, apparently not. So let me stop the recording.